and you're ready to go. Have a good session.
Yeah, thanks. Hello, everyone. Welcome to today's session on foundations. Our first talk would be on white box traitor tracing by Mark Zandri, and Mark will give the talk.
All right, thank you. So today I'm going to be talking about white box traitor tracing. So let us first recall the goal of traitor tracing. We have a content distributor who is broadcasting encrypted messages to a large set of recipients, whom each have their own personalized secret key. We are concerned that an unscrupulous user called a traitor may create and distribute an unauthorized decoder program that can also decrypt the broadcast. To deter such behavior, we want the content distributor to be able to trace the decoder, identifying the user that it came from. The bulk of the tracing literature has focused on producing schemes with shorter parameters, in particular ciphertexts, using various combinatorial and algebraic techniques. In this work, however, we will look at something different. We'll revisit the tracing model of essentially all prior tracing works. Specifically, all modern tracing works work in a black box tracing model, where the tracer simply queries the decoder on several ciphertexts and observes the plaintext that come out. The motivation for this model is that it allows for tracing decoders based on hardware, and also prevents us from having to decipher program code in the case of software decoders. To motivate our study, we will consider the following scenario. Suppose the identity of an honest user contains sensitive information, for example, a bank account number or something like that. A malicious user, or even the content distributor themselves, may be interested in trying to obtain this information, and they will try to extract it using a chosen ciphertext attack against the user's secret key. We show an impossibility that if your tracing algorithm is black box, that privacy against chosen ciphertext attack is fundamentally at odds with tracing. We show that any user who is able to trace, if the tracing algorithm is black box, can mount the tracing algorithm using a chosen ciphertext attack. We then complement this result by showing how to use functional encryption and non-interactive zero-knowledge proofs to build a scheme that maintains privacy even in the presence of chosen ciphertext attacks for honest users, but allows tracing against traitors. Because of our impossibility, such a result means that we need to use white box tracing, which means that we actually need to inspect the actual program code of the decoder rather than just viewing its input-output behavior. We next consider another scenario, which will also require white box tracing. Here, we consider a typical assumption in the multi-party computation literature, which asks for a reliable broadcast channel. This means if an adversary sends a message to another party, all parties will see the same message. There's no way for an adversary to send one message to one user and have that be interpreted as a different message for another user. This is important in many malicious MPC protocols, since we don't want a scenario where some users observe the adversary behaving maliciously, but others think the adversary is still honest. So we ask, what if the channel now is encrypted under a traitor tracing scheme? We show another impossibility in the black box tracing setting and demonstrate that any scheme with black box tracing in what I'll call a public tracing setting where anyone can trace, that in such a setting, the reliability of the broadcast channel is actually broken by virtue of it being encrypted with the traitor tracing scheme. In particular, an adversary can produce ciphertext which will decrypt differently to different users. We then complement this impossibility with another result. This one is a more limited result, showing that we can use fully homomorphic encryption and lockable obfuscation to get a traitor tracing scheme that is consistent. However, we only guarantee tracing under a constant number of colluding users. This is in contrast to many schemes that actually allow unbounded collusions. But nevertheless, it's sort of an initial positive result for consistent tracing. All right, and again, because of our impossibility, this result necessarily uses white box tracing. All right, this concludes the overview of my work. Thank you.
Thanks, Mark, for the presentation. Any questions from the audience? Feel free to ask questions on the chat or on the Zulip channel, or just simply raise your hand or
Mark, what's your model of white box tracing, like arbitrary, or you assume some specific format of the decoder, like some GGM or something?
No, the decoder is an arbitrary program, but you actually get the tracing algorithm actually gets the code for the program, as opposed to most of the work in the trader tracing setting where the tracing algorithm is only assumed to have query access.
So what kind of, I'm just curious, what kind of tricks do you use? Like Barak's kind of tricks?
Yeah, exactly. So the starting point is to use these unobfuscatable programs of Barak et al., which are programs that you can learn given the program code, but you can't learn just given query access. And then we have to, play some tricks in order to actually adequately embed these programs into the trader tracing system in order to get the guarantees that we need.
So I would imagine this is like beautiful observation, but I would imagine this is kind of purely theoretical. It has no hope to get something. Well, I'm just curious because in GG,
certainly
right,
certainly the constructions that we give are hopelessly inefficient. But there might be hope for either a different model or maybe using different techniques to get a more efficient protocol.
Well, because for some kind of schemes, the keys, it is reasonable to assume for some discrete log schemes that all the decoder keys do like different discrete log representations or something. So I would imagine it's conceivable to go into some kind of GGM or something, but I don't know if you thought about it. If you assume specific kind of programs.
Right. The problem is, I mean, I have thought about it. The problem is that at least so there is a body of literature, especially sort of in the early days of trader tracing, that did exactly this kind of thing, where you assume some structure of the key. For example, you assume that the trader actually outputs a legitimate key for the system. Mm-hmm. However, all of those schemes, as far as I'm aware, are very easily breakable if you are not restricted to such a legitimate key. So there's a question of what's the, making these restrictions, if it's really easy to just get around them by producing a fake key, by producing a general decoder program. There's sort of a question of what's really the guarantee you get from that.
Yeah, thanks.
Okay, great discussion. Let's thank the speaker again. And our next talk, Fermi, can you share the screen? The next talk will be, does Fiat Mirror require a cryptographic hash function, by Yilei Chen, Alex Lombardi, Fermi Mar, and Willie Quach. And Fermi is giving the talk.
Hi, everyone. Am I?
No, it's here.
Sorry, hold on. Let me unsh. Okay, sorry, is everything working with the slide?
Yeah, it looks good.
Okay, thanks. All right, so this talk is, does Fiat Mirror require a cryptographic hash function? This is joint work with Yilei Chen, Alex Lombardi, and Willie Quach. Alex and Willie are actually my roommates for the summer, so they're right next to me on hand to also help answer questions. All right, so this talk is about the Fiat Mirror heuristic, which in a nutshell is a magical compiler that somehow removes interaction from public coin interactive protocols. So let's recall that a public coin interactive protocol is an interaction between a prover and a verifier. The prover is trying to convince the verifier that some claim is true. They have a back and forth conversation where all the verifier messages to the prover are just random coins, randomized. And at the end of the interaction, the verifier either accepts or rejects just based on the transcript alone. And so Fiat Mirror takes such a public coin interactive protocol and turns it into a non-interactive protocol. And the way this goes is that the prover and verifier agree on something called the Fiat Mirror hash function H. And essentially what the prover is going to do is emulate a conversation with the verifier and then send over the resulting transcript to the verifier. But the way we're going to do it is the prover is going to compute the messages, the prover messages as it would in the interactive protocol. And then when it's time for the verifier to respond, what it's going to do instead is apply the Fiat Mirror hash function to the transcript so far and use that to compute the next verifier message. So it proceeds in this way, generating the whole transcript of interaction, sends it over to the verifier, and the verifier can easily check by just recomputing the challenges using the hash function and then accepting based on whether or not the verifier would accept in the original interactive protocol. Right, so this has been an incredibly fruitful approach to building crypto, both in theory and practice. The idea is roughly construct some kind of interactive protocol for a desired useful functionality, say identify yourself over the internet to someone. And then you apply Fiat Mirror to it to get a non-interactive implementation of the same functionality. And so this is an incredibly useful, really broad idea. But the problem with it is that a priori, it's not clear that even if you start with a sound interactive protocol, that Fiat Mirror is actually going to preserve soundness. So here's the intuition to keep in mind. You have an interactive protocol that is sound when these RIs, these random challenges, are in fact chosen randomly. So what the Fiat Mirror hash function A should guarantee is roughly that this shouldn't allow the prover to obtain favorable RIs, right? It shouldn't allow it to generate verifier challenges that will allow it to fool the verifier on a false instance. So there's basically been two classes of approaches for formalizing this in the literature. And you can show that, roughly speaking, whenever you would expect Fiat Mirror to work, you can show that when the Fiat Mirror hash function is modeled as a random oracle or a truly random function, that you can usually prove this. You can prove this in the random oracle model, that it will preserve soundness. And more recently, there's been a really exciting line of work giving sound Fiat Mirror instantiations in the standard model, in particular, identifying this property called correlation intractability, and showing that for a narrower but still interesting class of protocols, this actually suffices to get sound Fiat Mirror instantiations. But in all these cases, the Fiat Mirror hash function H is at its core a cryptographic hash function. There is some sort of cryptographic hardness associated with the hash function itself. And it sounds like a really natural thing for exactly what we're trying to do here, right? You don't want the hash function to allow the prover to get favorable RIs. So you want the hash function to have some sort of cryptographic properties that will capture this. In this work, we asked the maybe seemingly naive question, is this necessary? Right? Does Fiat Mirror really require a cryptographic hash function for sound compilation? And our first set of results are a set of perhaps surprising positive results, where we show that in fact, some protocols, some fairly interesting protocols can be compiled with really simple, non-cryptographic Fiat Mirror hash functions. And so what I mean by that, like what is a non-cryptographic hash function? I mean something like taking a vector of entries over ZP and spit out the bit decomposition of this vector. Right? So no cryptography, no one-wayness whatsoever. Or another example would be literally a linear function on the input. And we show that really simple Fiat Mirror hash functions like this, in certain cases, compile interesting protocols such as Lubitschewski's identification protocol, Schnorr's protocol, Sean-Peterson. And so these positive results are in a variety of settings. The Lubitschewski positive result we show in the plain model, whereas the group-based positive results we prove security in the generic group model. So we complement this with a set of negative results, essentially establishing some limitations on how far you can take this idea, how far you can go without putting cryptography into your Fiat Mirror hash functions. And we show that cryptographic Fiat Mirror hash functions really are necessary to compile a large class of 3-message honest verifier zero-knowledge arguments. These are really interesting protocols that we'd love to be able to compile with Fiat Mirror. And we show for this large class of protocols that cryptographic Fiat Mirror hash functions are necessary. So what do I mean? What is this large class? The important properties are that the first message of the protocol is pseudo-random, and the soundness of the protocol, this is crucial, the negligible soundness error of the protocol is achieved through parallel repetition of some base protocol where the challenge space size is small. This is really crucial to the result. So examples of protocols that satisfy these properties, for instance, classic protocols such as Blum's Hamiltonicity protocol, once you parallel repeat it, the GMW3 coloring protocol with parallel repetition, and even a 1-bit challenge version of Schnorr with parallel repetition. And this last example is really included to highlight the fact that it's not like some group magic that is making that's taking the cryptography out of the Fiat Mirror hash function. It was really the structure of the original Schnorr protocol. But here, when you get soundness through parallel repetition, even though you're using groups, you still need you still need cryptography in your Fiat Mirror hash function. Right, so in a little bit more detail, what we show is that if H is a sound Fiat Mirror hash function for such a protocol, then H must satisfy a cryptographic security property we call mix and match resistance. Essentially, this is a challenger adversary game you can write down about H. It has nothing to do with the protocol, it's just a property of H. And this game must have a statistical computational gap if you want H to be a sound Fiat Mirror hash function compiler. And in particular, we showed that this property implies one-way functions. Okay, so to sum up, the answer to our title question of does Fiat Mirror require a cryptographic hash function is sometimes. Okay, so for certain protocols, simple Fiat Mirror hash functions can be enough, but for many, many other protocols of interest, we show that cryptography is needed in your hash function. So our paper is up on ePrint, and highly encourage you all to take a look. Thanks.
Thank the speaker for the talk. And any questions from the audience? Feel free to unmute yourself if you have any.
Maybe I can ask, so if for those things where it is not necessary, it seems a very exciting result. So maybe I'm missing something. Like, does it mean that you don't need random oracles for Schnorr signatures, or?
Yeah, so okay, the answer to this is a little bit complicated. So there are certainly limitations. First off, it is a generic group result. And so we are saying that you really require optimal hardness from your group. And so if you really believe that your group has some sort of optimal hardness, then we are saying that yes, it is conceivable that you could have a sound or a sound Fiat Mirror compilation that just uses an information theoretic hash function. There are some caveats here where basically you show that when we say Fiat Mirror here, I guess I'm referring to compiling into an interactive identification protocol into a non-interactive ID protocol. But if I'm thinking about getting full signatures, which is the motivating practical application here, to actually get standard notions of signature security, you need a small message space. And actually showing that this can be made general requires the use of more complicated hash functions like random oracles potentially. In terms of like having meaningful practical applications right away, this result doesn't say that. It's saying, where does the security come from in the Fiat Mirror hash function? And we're saying that you can get some of the soundness, or you can get the soundness without needing crypto in your Fiat Mirror hash function, but you may need crypto somewhere else in the protocol. If either of you have anything to add, feel free to.
So this limitation about the message space, is that inherent? Like, is there an attack, or is it just a limitation of the current analysis?
I'm pretty sure it's inherent.
You can't like if your message space is larger than the size of the signatures, there's going to be some sort of collision attack on an information theoretic hash function. But we show essentially that if as long as the message space is not larger than the signature size, then information theoretic hash functions are okay.
Thanks.
Also, a quick question about the generic group model there. Is that Mars group or is it Shoops? Because Shoops comes with like a random function itself. I guess it's Mars when you say you model group with generic group model.
No, it is Shoops' generic group model. And I think that maybe the distinction here is that when you're talking about constructions, it makes a lot more sense to talk about Shoops protocol, Shoops formulation of the GGM versus Mars, because in Mars, so in this case, you actually need to apply the hash function, the Fiat Mirror hash function, to a group element. And Moore's model does not allow you to even specify what that means. So you need to have some kind of representation of the group element to even make sense of what it means to apply a hash function to it. And Shoops is of the two GGMs, the one that actually gives you representation to apply your hash function to. So yes, we are saying that the proof does rely on the fact that you are getting randomness from the group representation. But the hash function itself is still some really simple function, like literally like a linear function on that group element. So,
Thank you.
We have more questions from the audience, but let's push these questions to the end of the session after the third talk, because I just wanted to keep on time. And let's thank for me again, and we will take more questions at the end of the session. The next speaker, the next talk will be on composition with knowledge assumptions by Thomas Kerber, Agilus Kiayas, and Markov Kohlweiss, and Thomas will give the talk.
Thank you very much for the introduction. So yeah, this is on composition with knowledge assumptions, and I'm going to start with a brief recap of simulation-based composition, because that's the kind of composition we're really talking about. And in general, your security statements are something of the type that you want to show some real-world protocol here on the left is equivalent to some ideal specification. So in UC, for example, that would be your ideal functionality. And part of the simulation part of the simulation security comes from there being a smaller attack interface in the ideal specification, which a simulator translates into a larger attack interface to match what is available in the real world. And your security statement then usually comes in terms of this indistinguishability by saying, well, if we plug this in with some arbitrary environment or distinguisher belonging to some set of potential distinguishers, and I'll get into that in a little bit, then if you use the same distinguisher on both sides, the two are identical and they will behave identically when they're actually executed. And composition is then actually just a property of this set of distinguishers, because what you really want is you want to be able to move things in and out of this set of distinguishers. And if it's closed under the addition and removal of parts of the network, then you have composition, essentially. Now, with knowledge assumptions, I'm going to go with the example of the algebraic group model, which is a quite powerful knowledge assumption, but it illustrates quite well what you actually want them to do. And usually there, the statement is that whenever you're outputting some group element here, y, you need to know how to compute this from group elements you got as inputs. And the way this is usually formalized is to say that there needs to exist some extractor algorithm that, given all the same inputs, given the code to the algorithm you're running, and given its randomness, will be able to output the representation of y. So it'll be able to output something that explains further as to what's actually going on in the output of y. Now, if we look again at the compositional setting, where we want to use this usually is in the simulator. This is where we get some real-world cryptographic objects, and we want to extract some more information from that to be able to replicate it in the ideal world. Now, this is a problem because what that means, if we want to give the simulator access to this, is we have to give it the code and the randomness to the distinguishing environment. And that means we've removed all notion of privacy from our ideal world because we've given the ideal world adversary full access to everything that's going on. So we don't want that. And the solution that we have to this is to essentially allow the simulator to query, to do Oracle queries about the knowledge assumption and to essentially just do Oracle extraction queries. So in particular, we attach a type system to messages and we lift the distinguishing environments on both sides. And we say, first off, that it has to be something that supports the knowledge assumption. So we have to be able to extract. And then whenever it sends a what we call a knowledge implying object, so in the case of the AGM, just a group element, we transform that into a message which also sends the corresponding witness explaining how this was constructed. Now, that isn't what the other end of the network expects. So this message is then again intercepted, and just these pairs of knowledge implying objects and witnesses are recorded in a repository which the simulator has access to in the ideal world, but no one can access in the real world. And this is sort of the core of the idea. Now, one crucial thing that this distinction makes is it limits the set of distinguishing environments we can consider to a set of possible distinguishers. And interestingly, this cannot trivially absorb the simulator. So we have to change the algebra of composition to account for this. And we do this by making the sets of distinguishers explicit. And in particular for transitivity, that means you need to support absorbing the simulator for the first step. And for parallel composition, you need to be able to support absorbing what you're parallelly composing with. Now, for knowledge assumptions, what that means in practice is if you have disjoint knowledge assumptions K1 and K2, then you can get transitivity, provided you can lift one of the simulators so you can extract from it. And if you are parallelly composing, if you can extract from what you're parallelly composing, then that's also fine. We have impossibility results if you don't do this generalization. So there are some special cases where it does go through, but in general, there are counterexamples, and we give those. And we also have as our main motivation that we want to be able to show the composability of snarks, and we do that for the Groth16 ZK snark, which recently was shown to be simulation extractable. And we show that with special case analysis, you can also do secure setups for these. Now, there are still a number of open questions. In particular, a lot of algorithms which use knowledge assumptions aren't designed with simulation extractability in mind, and this is something which we find very interesting and which should be explored more. And also, our results show an explicitly show a negative result for reusing knowledge assumptions generically. In practice, we see this is done quite often, especially with groups. We see that they are reused quite frequently, and then the algebraic group model is applied to them. And this is something which our result does not immediately show is safe, and we believe there needs to be further analysis to see when is it actually safe, and is current practice good in that regard. That's it. I'll take questions now.
Let's thank the speaker for the talk. Any questions from the audience for Thomas? Okay, let's thank the speaker again. And we will take more questions for Fermi's talk. There is one question on the chat from Ashrit Gosha. Can you characterize the set of protocols to which the part 1 result applies beyond these specific examples?
The short answer is no. It was sort of a case-by-case basis. We can characterize the protocols that it doesn't apply to, but no, getting the boundaries of what protocols we can actually have positive results for is not something that we do.
And there are more questions on the Zulip channel. I saw that Lawrence's question is already handled. Do you have more questions, Lawrence?
No, he answered my question good. Well, thanks.
Okay. And there is a question from Tal Malkin. How does mix and match resistance relate to standard collision resistance?
You wanted to answer this one?
So mix and match resistance is black box separated from collision resistance. So that in this, mix and match resistant hash functions do not imply collision resistance. And the reason is that mix and match resistance, one way to instantiate it is by using a form of what's called single input correlation intractability, while collision resistance is a form of 2 input correlation intractability. And this is these are black box separated.
Okay. The next question is by Watson Lad. Do these results apply to all the discrete log statements? I think Schnorr considers somewhere and ends and ors, etc., or just a proof of knowledge of a single discrete log.
Not that we know of. We handled Schnorr, we handled Chom-Peterson, which is about equality of 2 different discrete logs. But we did not. There's no such general result for ands and ors. Yes.
Watson, do you have more questions, or does that answer your question?
Can you do some, you did equality, but can I also do linear relations? Or
That's a good question. It's not something that we tried to answer at all.
Okay. The next question is by Stanislav Jiraki. You discussed soundness of the resulting NI protocol, NI proofs, but what about their ZK properties given your instantiations of the hash functions?
Yeah, the ZK properties in most cases are just easy to achieve by standard techniques. You randomize the hash function in some way.
Yeah, zero knowledge for Fiat Mirror protocols is usually easily generically obtainable, which is why we weren't focusing on it in the talk or for like the introduction of the paper, but you can do it.
But you don't mean that using these hash functions is zero knowledge. You mean that some compilation applied to it?
Yeah, if you XOR with the random mask, you should get zero knowledge or something like that.
Yeah. So take one of the simple ones and then put in a key, and the key is just XOR the output with the random string is just the key.
Of course, you need some sort of program, like some place to program for a zero knowledge simulator, and these hash functions won't, in our positive results, won't have any place for that. So you need to, yeah, add this mask for programmability.
Okay. Do you have that in the paper? Examples of that? Because,
yes.
Okay, great. Thank you.
Okay, cool. Any other questions? Yeah, go ahead.
So on an intuitive level, so you said you can prove security of Schnorr signature or something like that in generic group model, right? If you instantiate the hash functions as some kind of linear function in the generic group model, assuming I understood it correctly, what's your interpretation? Is this, something that for some groups you recommend to do?
Okay, this is a really good question, okay. So actually, we first proved a generic group results, and I guess you can make of it what you will. And then we found that actually there are like fairly reasonable non-uniform attacks on the resulting signatures. And then we found that not only are there non-uniform attacks, these non-uniform attacks are efficient for like widely used groups like ZP star elliptic curve groups. So what we actually found was that the way to handle these sort of attacks was then to prove security in the auxiliary input generic group model. And this we can have a little bit more confidence in. And we actually do give a concrete proposal of like the simplest Schnorr signature that we do not know how to break. I wouldn't say that we have like enormous confidence in it, but it's just we wrote down a candidate in the paper, a ZP star based Schnorr signature with a very simple Fiat Mirror hash function, and we don't know how to attack it. So it might be just a nice place to start thinking about what these results actually say for concrete groups.
But on intuitive level, yeah, it's just it's not clear if I mean, I understand you have to be careful about non-uniform attacks, but it's not clear which one would you recommend overall, like your scheme or a standard one. Standard one, I guess, has more confidence. My intuition is the proof must be more complicated, right? Those GGM proofs are a little bit more complicated than random oracle proofs. To me, I'm hoping that because the proof is more complicated, maybe it tells you more about security, but I'm not sure.
Yeah, I don't think I would go that far to say that. Yeah, as for what the intuition here is, I guess like just, I mean, the more confidence you have in the hardness of your group, so maybe you might have more confidence in certain elliptic curve groups than you might over ZP star. But beyond that, I'm not sure what else.
Yeah, I think so. For me, the main like takeaway from this class of positive results is that it's possible to argue the soundness of a Fiat Mirror protocol by making use of hardness properties that are really just about the interactive protocol rather than the hash function. So in the case of like Schnorr, the interactive protocol is about this group. And it turns out that you can use hardness properties of the group itself to argue the soundness of the Fiat Mirror version. And so it's just the hardness is coming from a different place than in the random oracle model Fiat Mirror protocols.
Yeah, very nice.
Yeah, one thing you can imagine, for instance, is like making a really, really like close to optimally hard group using IO and crazy things. Like using PRFs to generate the labels of your group and then using IO to handle the group operations. And you could hope that maybe this approximates a generic group in some way. And I guess we might expect that our positive results might more faithfully capture reality for this kind of super, super hard group versus a more natural group.
Thank you, guys. Yeah, nice. Very nice result.
Okay, let's thank Fermi and Alex for taking all the questions. We will take